Hello, everyone. Today, we are going to talk about 4 questions need to be answered when you construct a short control chart. They are how to determine the upper contour limit, lower contour limit, how to decide the sample size, how to estimate mu0 and sigma 0 if they are not given, and how to evaluate the performance of the control chart. Let me start with the first one, how to determine the upper contour limit, lower contour limit. To answer this question, we regard a control chart as a sample-by-sample hypothesis test between null hypothesis saying that a process is in control and alternative hypothesis saying that a process is out of control. Any hypothesis test involves 2 types of errors. Type 1 error, say alpha error, and type 2 error, say beta error. Between these 2 types of error, type 1 error is related to the upper contour limit, lower contour limit. Actually, the basic idea to choose upper contour limit, lower contour limit is to achieve a desired alpha error level. In the previous lecture, when we talked about 5 procedures, the 5th step was about decision rules, saying that if the sample statistic is not included in the control limit, we conclude that the process is out of control. That means the interval smaller than lower control limit and larger than upper control limit is out of control region. This concept is very similar to rejection region in hypothesis testing. In hypothesis testing, the rejection region is the interval measured in the sample distribution of the statistic under study that leads to rejection of the null hypothesis. As we know, the probability to reject null hypothesis when null hypothesis is true is denoted by type 1 error, and the rejection region is determined to be the type 1 error becomes the predetermined level of alpha. In similar way, we can determine the upper contour limit, lower contour limit to make the out of control region to be predetermined level of alpha. Formally, we can show that the relationship between alpha and control limit, let z be a standard normal variable computed from distribution of x bar. Then by definition, alpha is the probability to reject null hypothesis given null hypothesis true. Rejecting null hypothesis means that x bar is in the rejection region, which is the interval smaller than lower contour limit and larger than upper contour limit. On the other hand, that null hypothesis is true means the process follows normal mu0 and sigma 0 square. With some calculation, alpha becomes the sum of 2 terms. The left term is the probability to reject null hypothesis because x bar is larger than upper contour limit, while the right term is the probability to reject null hypothesis because x bar is smaller than lower contour limit. If we choose lower contour limit and upper contour limit to be symmetric about mu0, then we obtain some formulas about upper contour limit and lower contour limit respectively. As a result, upper contour limit is mu0 plus z alpha over 2 times sigma 0 divided by square root n, and upper contour limit equal to mu0 minus z alpha over 2 times sigma 0 divided by square root n. As the formula indicates, the width of control limit is determined by alpha level via z over alpha, sigma 0, and sample size n. typical value of z alpha over 2 is 3 for simplicity. So if z alpha over 2 equals to 3, then the corresponding value of alpha can be computed to be 0.0027. Then second question is about how to choose the sample size. The sample size can be determined to meet the desired level of beta error. Let me explain why. Let's consider a situation where we want to detect a mean shift to mu1. Usually, the difference between mu1 and mu0 can be modeled by k times sigma 0, where k is a constant. As we learned in the previous lecture, control chart detect the change in underlying distribution. For mean shift, the distribution of x bar is changed to normal mu1 sigma 0 square divided by n. Since beta is the probability to accept null hypothesis given null hypothesis false, we end up with this beta function after some computations. As you see, the beta error depends on the value of alpha error, the magnitude of the mean shift k, and the sample size n. Their relationships are as follows. As alpha decreases, beta increases. This makes sense because alpha error and beta error have a trade-off relationship. As n increases, beta decreases. In other words, more information from the data helps reduce the beta error. As k decreases, beta increases. This makes sense because the small magnitude of mean shift is more difficult to detect. These relationships can be graphically illustrated using the operating characteristic OC curve. The x-axis of the graph represent k, and the y-axis represent the value of beta. As you see, we can easily check the beta error decreases as n increases and k increases. And note that this OC curve includes the information of alpha as well. The value of beta when k equal to 0 represent 1 minus alpha. This example problem is about how to determine the sample size using the beta function. Suppose we wish to test the hypothesis with null hypothesis saying that mu0 equal to 45. Sigma 0 square is known to be 16, and we want to detect a mean shift to mu1 equal to 50. And then what sample size must be used to ensure that the probability of type 2 is no greater than 0.1? To solve this problem, we need to find the value of k. Since mu1 equal to mu0 plus k times sigma 0, k equals to 50 minus 45 divided by 4, which is 5 over 4. Then with 5 over 4 and alpha equal to 0.05, we can find the sample to make the value of beta must be less than 0.1 using the OC curve. Third question is about what if target parameters are not given. In previous example, we assumed that mu0 and sigma 0 are given. For example, upper contour limit, lower contour limit formulas involve the target parameters. To answer this question, we need to estimate them from a set of historical data or training data. Once they are estimated, then we treat the estimated values as if they are given. and substitute directly into the previous formulas. Let's revisit the hard-to-bake process example. Suppose these 25 samples are historical data. From each sample, we calculated sample mean and sample range. By taking an average of those 25 sample means, we can estimate mu0. Similarly, we can estimate sigma 0 by using the average of sample ranges or sample standard deviations. Here, D2 and C4 are known value given the sample size n. They will be covered in the next lecture. As you see, we can estimate target process parameters from data. Short control chart always use an X bar chart in conjunction with either an S chart or R chart. Historically, R chart was more popular because it is relatively easier to compute. Of course, this kind of computation is not matter anymore today. Today, S is more preferable because S chart is more efficient and informative. The fourth question is how to measure the performance of a control chart. Considering that a control chart is actually a series of sample by sample hypothesis tests, we need a more intuitive and more direct measurement of performance. For that, people use the average run length, ARL, as a performance measure of control chart. As the name says, ARL is the average of RL. Then what is RL? RL is the sample number on which a control chart first signals. That is, RL is the sample index when a data point is outside the control limit for the first time. Note that the run length is actually random variable. It can take any non-negative integer values with some probability. Therefore, we need to use this expected value as a performance comparison measurement. The expected value of RL is called average run length. There are two types of ARL, depending on whether the process is actually in control or out of control. In control ARL, ARL0 is defined as the expected number of sample until control chart signals under the condition that the actual process is truly in control. While out of control ARL, ARL1 is defined as the one under the condition that the actual process is out of control. Consequently, we'd like to ARL0 to be as large as possible and ARL1 to be as small as possible. ARL0 for short control chart can be computed analytically. For example, in mean shift detection, since the probability X bar is outside of the control limit under the condition that the IC process is alpha, the probability X bar is inside of the control chart is 1 minus alpha. Then we can calculate the probability RL to be 1, which is alpha. The probability RL to be 2 is the probability that the first sample is within control limit times the probability that the second sample gives a signal, right? So it is 1 minus alpha times alpha. So in general, we can calculate the probability RL to be K, which is 1 minus alpha power to K minus 1 times alpha. Then we can calculate the expected RL by using the definition of expectation. ARL 0 is summation over k equal to 1 to infinity on k times probability that ARL that RL equals to k. With some computation of sequence, we can obtain that ARL 0 equals to 1 over alpha. In similar way, we can calculate ARL 1 using the value of beta. Since probability X bar is within control limit under the out of control process is beta, we can compute RL equal to K, which is first K minus 1 samples are outside control limit and K sample gives signal. With some computation of sequence, we can obtain that ARL 1 equals to 1 over 1 minus beta. As you see, for Schwartz control chart provides ARL 0 and ARL 1 that can be computed analytically by using alpha and beta respectively. Let's try to compute ARL 0 and ARL 1 with an example. Let's consider X bar chart with in control mean and standard deviation, mu 0 equal to 30 and sigma 0 equal to 1.5, and sample size n equal to 5. If the 3 sigma control limits are used, then what is alpha error? In the previous slide, we showed that the corresponding alpha error is 0.0027. Then what is the in control ARL? ARL 0? If we apply the formula of ARL 0, then it is simply 1 over alpha. So ARL 0 is around 370, which means that we expect to see first signal in the 370 sample on average if the process is in control. If the process mean shift to mu1, 32, then what is the beta error for the chart to detect such a shift? What is the out of control ARL, ARL1? Since alpha, n, and k are given, we just plug them into the formula of the beta function. Then we obtain the value of beta to be 0.51. Since ARL1 equals to 1 over 1 minus beta, so ARL1 is 2.04. From this example, we obtained around 370 ARL0 and around 2 ARL1. This is pretty good because 370 is a relatively large number, and 2 sample delay in detection is not serious. As you see, using ARL, we can evaluate the performance of the control chart. So a control chart having larger ARL0 or smaller ARL1 is preferable. Let me point out the effect of sample size on ARL. As the sample size increases, it is known that both alpha error and beta error decreases. Therefore, ARL0 increases and ARL1 decreases. Consequently, the performance of control chart improves. However, a large sample size may delay the detection of change because collecting sample takes time. In addition, it may increase sample cost. So in practice, the sample size 4, 5, 6 are typical choice for balancing between obtaining desirable ARL and keep the sample cost low. Before finishing today's lecture, I want to mention one drawback of a Schwartz control chart. Suppose we use n equal to 5 and want to detect k equal to 0.5. Recall the previous result in which ARL1 to detect mean shift of k equal to 1.33 was around 2, right? With k equal to 0.5, it turned out ARL1 becomes 33, which is quite slow in detection. This is because a Schwartz control chart has no memory. That is, Schwartz control chart always use the latest update of process measurement instead of utilizing the information embedded in the entire sequence of measurement. We will learn other control chart which overcome this limitation that Schwartz control chart has. Thank you.